Continuing with Chapter 17, we're going to talk about the binomial model today. We're going to go back to the Tiger Woods card. Suppose we want to know what the probability is that you buy 5 boxes of cereal and you get exactly 2 Tigers cards. This time, we're interested in the number of successes out of 5 trials. And that's kind of the difference between a binomial and a geometric model. In the geometric model, we're interested in when a success occurs, but in the binomial model, we're interested in how many successes occur. So to try and determine if you should use the geometric or the binomial model, it's helpful to ask yourself, is the problem asking you when the success will occur, or is the problem asking you how many successes will occur? Because that's the big difference. So in this particular case, we want to know the probability that the number of successes is 2. This is an example of the binomial model, again because we're interested in how many successes. So the binomial model is defined by 2 parameters. The first is based off of the number of trials, which we define as n. The second is the probability of success, which again is denoted with a lowercase p. The overall notation is going to be binom and then in parentheses, your number of trials, comma, your probability of success. In this particular example, we have 5 trials, so n is 5, and our probability of success is still 20% or 0.2 because that was the probability of getting a Tiger Woods card. So in this particular case, we would think that since we will have 2 successes, well, out of 5, that means we're going to have 3 failures. Therefore, we would take our probability of success and square it and multiply it by our probability of failure to the 3rd power for the number of successes and the number of failures. The issue with doing that is that it doesn't take into account the order that we could get the cards. We could open up 5 boxes of cereal, and in the first 2 boxes that we opened, we got Tiger Woods card. Or maybe it occurred in the first box and the last box, or the second and the 4th box, or the 3rd and 4th. Any combination could result in 2 successes and 3 failures. That means that we need to take into account all the possible orders in which the outcomes can occur. We could use addition to add up all the different probabilities, but a problem occurs when you have a high number of trials and it becomes too much work. Even in this particular situation, we're still going to end up with 10 possible outcomes, which means we would have to add up the probabilities 10 different times. But if we have 200 trials, now we're talking about thousands of possibilities, and that's just too much work. Therefore, we're going to end up using a combination. A combination takes into account the number of possible ways an outcome can occur using the n number of trials and the k successes. So we're going to use the letter k to represent how many successes. So the total number of ways that can happen is written as n over k in parentheses, or nck, which is pronounced n choose k. So number of trials, choose number of successes. So this looks really scary, but I don't want you to worry about it because we're not actually going to do this math. I'm just pointing out right now what doing a combination entails. So n choose k is the same thing as n factorial divided by k factorial times n minus k factorial, where doing factorial means that you start with the number and multiply all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. When you do this, we end up with 10. Now don't worry, our calculator will actually do combinations for us, but we won't even need it to because we'll end up using the binom PDF and binom CDF similar to the geometric way that we did it on our calculator. But back to the particular problem, there are 10 possible ways to get 2 Tiger cards in 5 boxes. Each of those probabilities is going to be 0.8 to the 3rd times 0.2 squared. Therefore, the probability of success being 2, it would be equal to 10 times that probability, which ends up being 0.2084 or 20.48% of the time. In general, the probability of exactly k successes in n number of trials is given by that formula, where you have n choose k times p to the k, which is your probability of success to the number of successes, times q to the n minus k, which is the probability of failure to the number of failures. In general, the binomial model for Bernoulli trials is going to have the notation of binom, then in parentheses, number of trials, probability of success. Again, n is your number of trials, p is your probability of success, q, which is 1 minus p, is the probability of failure. K is going to be the number of successes out of your number of trials. Therefore, the probability that x equals your number of successes is going to be n choose k times p to the k times q to the n minus k. Your mean, to calculate the mean for a binomial model, it's going to be n times p. And the mean would calculate on average how many successes you would have in that many number of trials. And then the standard deviation is the square root of npq. All three of these formulas will be given to you for your test because they're given to you on the AP test. For example, suppose that 20 donors come to the blood drive. So we're going to go back to the blood drive example from before. In our blood drive example, the probability of having O negative blood, so the probability of success, was 6%. So P equals 0.06. This means that Q is equal to 0.94. Number 1 wants to know what are the mean and standard deviation for the number of O negative blood donors. So out of 20, how many do we expect to have, and then what is the standard deviation? To find the mean, mu, that's equal to n times p, your number of trials times your probability of success. The number of trials is 20, and the probability of success is 0.06. When I multiply those together, I get 1.2. So out of 20 donors, on average, we'll have 1.2 people that have O negative blood. So really probably only about one person. The standard deviation, or sigma, is calculated as the square root of npq. Number of trials times probability of success times the probability of failure, taking the square root. So this would be the square root of 20 times 0.06 times 0.94, which ends up equaling 1.06. So again, this gives us that the average number of people out of 20 that will have O negative blood is 1.2, with a standard deviation of 1.06. Our second question is asking us, what is the probability that there are 2 or 3 universal donors? So this is going to be the probability that our number of successes is 2, or our number of successes is 3. Since I'm using the word or, that indicates I'm going to add, so this would be the probability of having 2 successes plus the probability of having 3 successes. Using the formula n choose k times p to the k times q to the n minus k, for the probability of 2 successes, this would be 20 choose 2 times 0.06 to the second power times 0.94 to the 18th power, plus the probability of 3 successes would be 20 choose 3 times the probability of success to the third times the probability of failure to the 17th. So this ends up equaling, so the probability that you get exactly 2 successes is 0.225, plus the probability you get 3 successes is 0.086. So it gives us an overall probability of having 2 or 3 successes as 0.311. So in other words, there is a 31.1% chance that out of 20 donors, we will have exactly 2 or 3 universal donors. This is it for tonight. We're going to go over how we can do this on our calculator, as well as how to still show work, because all of the work I've shown here is still going to be required, but it will be easier to do on your calculator, and we'll go over that tomorrow in class. But we're done for tonight, so have a good night.